So let's continue chapter 9. This was a chapter about entropy. So let me just start by recalling what we have seen before, like in the last lecture. So this is a chapter we started just last lecture. We might spend 2 more lectures on this. So remember, we have our probability space. So this is a topological space. You have a Borel sigma algebra, and you have a measure, probability measure, okay? Measure space. And we have a dynamical system. The least condition we put is just measurable, okay? This is measurable. And in general, we choose, as we were doing, we choose P is a measurable partition. So it is, I only use countable partitions, okay? This is a countable partition, measurable partition of M. Okay? And remember, we have defined the entropy of a partition, which doesn't use any dynamics. So this is just respect to the measure mu, which is the sum of P. You sum over the partition element mu of P log of mu of P. Okay. So this is the definition of a partition, of a entropy of a partition, and we have seen few properties of this, like we have the relationship between, like we define the relationship between partitions. One is finer than other, and so if a partition is finer than the other one, that finer partition will have bigger entropy. So you will have more information from that partition with respect to your space and the measure. Okay, and we have defined entropy of a dynamical system now with respect to a given partition. Entropy of F with respect to P, to the partition P. And this was H mu Fp. And this is the limit when n goes to infinity of 1 over n H mu Pn. And remember, the definition of Pn is, the join using the dynamics. Okay, recall that Pn is just the join I equals 0, n minus 1, f minus I of P. Okay, and this is, the elements of this are just intersection of elements of these partitions, okay? So obviously you see that in particular, Pn is coarser than Pn plus 1, okay? Pn is coarser than Pn plus 1. Okay, and now the metric entropy, we have defined also the metric entropy. Metric entropy. This was just the entropy of, metric entropy of a dynamical system. Okay, it's the entropy with respect to a measure, and this is the supremum over the entropy with respect to partition, P partition, okay? Just measurable, okay? As we said last time, just looking at this formula, it might be very difficult to calculate the entropy, the metric entropy of a dynamical system, because if you want to check this quantity for all partition, that's not something I'm willing to do. And so there are some theorems that gives you another way to evaluate this quantity. And last time we end the course with Kolmogorov-Sinai. See now as theorem. It's just a recall, so we stated last time, that's where we stopped our lecture last time. So this says that if you have a family, a sequence of partitions that are non-decreasing, and so on, if this such that, and if this generates the sigma algebra, Pn generates the sigma algebra generates B, then you can just calculate this using this sequence. Then H mu of f is the limit when n goes to infinity of H mu f Pn. Okay. So this is the term that we want to prove today, and also do some applications like to the Gauss maps and others. Yeah. So we will be proving this theorem today and some applications of it. And yeah, before that there are some preliminaries that we want to do. So remark that you see that this quantity here is less than the entropy by definition. This guy is less or equal to, so by definition, the limit, the entropy is greater or equal to the limit when n goes to infinity of H mu of Fpn. Okay, this you can see because this is the supreme of all partition, and yeah, you have this for free. So now to prove this, you want to prove the Auger inequality. Okay, so enough to prove that for every partition. So I forgot to say that all these have finite entropies. Okay, enough to prove that for any partition, Q, we have that the limit on n on a of H mu f Pn, this guy is bigger than H mu fq. Okay, so this is what we want to prove, and yeah. So before we start the proof, let's do some preliminaries. One is this proposition. For any partition, Q with finite entropy, there exists a partition on the algebra. Okay, there exists a partition P. A is algebra, okay? That is just given by countable union and intersections. For every partition and every epsilon positive, so every epsilon positive, there exists a partition P that is, the elements are in the algebra, okay? I mean, the way why we introduce this algebra is usually when you are, for instance, on R, you want to do this calculation, it's easier to take elements that are just intervals. And we see that the intervals, they constitute an algebra that generates the sigma algebra, okay? Such that H mu Q knowing P is less than epsilon. Yeah, see that this is just telling you that if you give me any partition with finite entropy, I can approximate it with partition whose elements are in the algebra. Yeah, you can have an approximation. Yeah, basically that's what this is saying, okay? Because the information you get out of Q, knowing already P is small, so that means that these two partitions are nearby in terms of, you know, in terms of the information they have, okay? So now let's prove this. So the way to prove it, so I said that I'm only considering countable partitions, okay? So you can write Q as Q1, let's say I, for I equals, we just index the elements of Q, okay? These are at most countable. I was using J here. So J in N, if it is finite, you just, you know, stop somewhere and you keep repeating the first part you have. So we defined an element, this partition Qk. So given K in N, you define Qk as this partition that is given by Q1, Qk, and the last elements you take as Q0, we call it Q0, that is M minus this union. J equals 1 to K of Qk. So this is just to make it like a finite partition. And yeah, it is obviously a partition because you take the union, give the whole thing, and so on. Yeah, it is clearly a partition. And see that this partition is an approximation of this one. That's you know, written in this claim that the limit when K goes to infinity of the entropy of Q knowing Qk is 0. And somehow this partition is an approximation, as you can see by construction. Okay, let's now try to prove this claim. So proof of this claim, in fact, let's just write the definition of this quantity, okay? H mu of Q knowing Qk. This is the sum for, so I'm summing over Qk. Qk, it has K elements, so for I equals 0 to K, and the sum for J bigger than 1, because these are elements and the natural numbers, of mu of Qi intersect Qj. This is just the definition, okay? Log of mu of Qi intersect Qj over mu of Qi. Okay, yeah, I is the guy in Qk. And one has to look at that this sum, you know, for J less than K, for J less than K, you see that either this quantity is 1, which would mean that this guy is 1 and this is 0, or this quantity is 0 and you will have here 0 and here also 0, and the polynomial dominates the logarithm, so you see that this will be 0. So for all for all j less than k, this is 0. Okay, so you can reduce this sum as the sum for j bigger than k of, and in that case, what you would have here is just mu of qj log of mu of qj. Yes. Sorry, here you would have mu of q0, sorry. Okay, because j is going from 1 to, yeah. Because, okay, so this start with 1, okay. All right, and you can see that this is less or equal to the one without this denominator, because this is, I forgot the minus sign here, sorry. Mu of qj log mu of qj. And this is the tail when you write the entropy of the partition Q. So this is the sum where j goes from 1 to infinity, okay? So this is the tail of that sum. So Q having finite entropy, so that sum is converging, so the tail should go to 0 as k goes to infinity, okay? So this goes to 0 as k goes to infinity, okay? Because this is a tail of a convergent series. Yeah, so yeah, obviously, yeah, this you can see just by construction that this guy will approximate this one. But this is not what we want. We want something that is in the algebra. Okay? Now let's back to the proof of the proposition, okay, this proposition here. So how we do this proof, we take on let epsilon, so epsilon is given by the proposition. So we want to construct the partition P, which will depend on epsilon. So first of all, we choose k large enough such that this is less than epsilon over 2, because this goes to 0. So for k large enough, it gets small. H mu of q, qk, epsilon over 2. That you can do. Now you fix some delta positive, and now you want to, so this is something I think I discussed in the previous lectures, that every you have it also in your course on measure theory, that every measurable set can be approximated by, sets that are in the algebra. So this is just saying that we can choose. Now we are just dealing with finite partition. Okay, fix. So for every I, for I in 1, 0 to k, there exists AI and elements of the algebra such that this approximates the QI, such that the measure of AI, the difference symmetric with QI, is less than, I think the constant, k squared, just to have everything. Oh, sorry, there's no delta here, so it's the same epsilon I'm using. So epsilon over 2k squared, okay? Now one could think that these elements, AI, would do the job you want because they are in the algebra, but they are not yet a partition, so you just have to make them disjoint. So you do this usual procedure. So you take P1 equals A1, and Pi equals AI minus the union J equals 1 to I minus 1 of Aj for I equals 2, and so on. Okay. Now from this you can see that the difference symmetric between Pi and Qi is also small, like the measure of that. So observe that pi ai is a subset of the union from j equals 1 to I of a j different symmetric with qj. Okay, this is something you can have, and you can easily see now that the measure of pi ai will be less or equal to the sum j equals 1 to I aj qj, and that's the motivation why we put here k squared, because this is at most k, and this will be less or equals epsilon over 2k. So finally what you have is, you have that h mu q knowing p. So p is a partition given these pi's. So this guy will be less or equal to h mu of q knowing qk plus h mu of qk. This is one of the knowing p. This is one of the inequalities we have proved last time. And you have three partitions. You have this inequality, which also in terms of information, it makes sense. We discussed that last time. And you can see that this is less than epsilon over 2 plus epsilon over 2, which is less than epsilon. So you see that you have the partition. We go through this just to make this partition finite. So if Q was finite, you would not need to do this part. You could just approximate any elements by an elements of the algebra. Okay. So corollary of that so let me recall that today we will be proving this part, and what we are doing are just preliminaries about the proof. Okay, corollary. So where am I? Yes. So let Pn. So this is as in Kolmogorov of Sinai, this here, as in Kolmogorov of Sinai, this statement. So P are non-decreasing, and the union generates the sigma algebra. Then the limit when n goes to infinity of h mu of q knowing Pn equals 0 for every key with finite entropy, okay? For all key with finite entropy. So remember, this is used here. Okay, this was used here, the fact that Q has finite entropy. Okay, so let's prove this corollary. So you can consider the algebra generated by these guys. So let A and B the algebra generated by the union J equals 1 to n of Pj, and A as this guy, this countable union of An, and this is generated by this guy, Pn, okay? Okay, now we know the statement, so forgot to remember. Yeah, from what we've seen, we know that for every epsilon positive that exists P that is in this, that is in the algebra, like a partition whose elements are here, such that H mu Q P is less than epsilon. So this is what we have just seen now. So since this guy, it's like this guy being finite, I forgot to see that, yeah. In this construction, we have seen that the cardinality of P is finite. I'm sorry, it was not in the statement. But you can see from the proof that we just have finitely many of them, okay? The cardinality being finite. So this means that P is coarser than Pm for m large enough, okay? Yeah, think of this property that this guy generating the algebra, it just means that the elements are, smaller and smaller. When m goes to infinity, this guy will be coarser than this one, okay? So for n bigger than m, we have h mu of q knowing Pn is less or equal to h mu of q knowing Pn. This we know. Pm here, okay, this is m. Yep. And this is less or equal to because I remember if so if you know Pm, you know more information. So what is left to know is smaller, okay? Is smaller in terms of information. Yep. H mu of q knowing P, this guy is less than epsilon. That's what we have. So this implies, so you have it for all n bigger than m, you have it for, so if you take epsilon going to 0, that means that you just need to change your m. So this implies that the limit when n goes to infinity of h mu, this guy is 0. Okay, now we can start the proof of Kolmogorov-Sinai. After we have this corollary proof of Kolmogorov-Sinai, yeah, now it's just easy. It's just a small application. So from the relationship we proved last time, so given any partition Q, you have this. Knowing Pn plus h mu of Q knowing Pn. So for every epsilon so for every epsilon positive, you can choose n large enough such that this guy is less than epsilon. So there exists n naught such that you have h mu of fq less than h mu of f Pn plus epsilon. is for all n bigger than n naught. And this is just to tell you that this is less than the limit, okay? So Kolmogorov-Sinha is a tool to calculate the entropy in some cases. Like you don't need to check the entropy of all partitions, but if you have a sequence of partitions that is non-decreasing and the union generates the sigma algebra, then you are okay. So now a corollary. That let P be partition of finite entropy such that Pn, which is a join I equals 0 n minus 1 f minus I p, generates the sigma algebra then h mu of f equals h mu of f p, okay? Yeah, this is just an application of Kolmogorov-Sinha when you just use Pn equals, yeah, so apply Pn equals this partition, okay? Yeah, so this is a corollary that applies to the full branch map. If you remember, last time I take this example, f of x equals kx mod 1, where k is an integer bigger than 2. So you can see that the entropy of Lebesgue, of the dynamic system with respect to Lebesgue, is just log k. You can apply this easily to see that. Last time, we just stopped at the entropy of the partition that is given by, that you get from the definition of full branch. That guy is log k, but that partition will also realize the supremum, okay? You can use that to calculate the entropy of the total. Another corollary is that if you have a partition like in Kolmogorov-Sinha theorem, a sequence of partition, non-decreasing, such that the diameter, so now I'm putting a metric space, so let's suppose that M is a metric space, M. Is a metric space, and you have a sequence of partitions, so on, such that the diameter of P in X goes to 0 as n goes to infinity. So P and X is the element diameter. P and X is the element of the partition that contains X, okay? For mu almost everywhere, for mu almost every X, then this guy will realize the entropy. The entropy of F is the limit when n goes to infinity of h mu of F Pn. Okay, P and X is the elements of the partition that contains X. Okay. Yeah, the idea, the proof of this corollary is just using the fact that from this diameter going to 0, you can see that you can guarantee that the union of Pn generates the sigma algebra, and you use Kolmogorov-Sinai. Okay. Okay. So let me write. I did not say P and X is the element. So I said the element is the element. It's almost everywhere, okay? It's the element. The is, because X, this is a measurable partition, okay? So the elements of Pn that contains X. Okay? And the proof is, check that diameter of P and X goes to 0 implies that Pn generates the sigma algebra. Okay? There's this exercise which is nice to do, to check, that if you take a covering map, let F on the circle, this is a covering map, of degree D, and mu be F invariant, then the entropy of F with respect to me is less or equals to log D. This is an exercise you can check. Or maybe let's just maybe do a very explicit example or a baby case of this exercise, which is just, a doubling map. F of Z is Z squared on S1. So this is a covering map of degree 2. You have any, this is a covering map on S1, map of degree 2. You can write a partition of 2 elements, so Pn. So this is just like 2x mod 1, okay? If you want to be more explicit, this is just like 2x mod 1. But just in a flavor of this exercise here, P is I1, I2. These are just 0, half, and 1. And you can see that Pn, the partition Pn, will have 2 to the power n elements. So you will have I1n, I2n, n. And see that the diameter of these guys goes to 0 of I, n, x. Yeah. This is of size 2 to the n, 1 over 2 to the n. Yeah, so this is 1 over 2 to the n. It goes to 0, so, and you can see that by Kolmogorov-Sinai that, or this corollary, sorry, this one. This corollary here, you can see that the entropy of Lebesgue is log 2. I think today I will not get to more applications of this theorem because we have the Gauss maps and other examples that we will do probably on Wednesday, next lecture. So let me discuss a little bit about the dependence of this entropy with respect to the measure. So dependence, so this map mu gives H mu F. So you fix your dynamics and you're changing the measure. Okay? So here we know we have a topology, okay? So here we have a weak star topology, okay? We know this topology. These are real numbers, okay? This is R, okay? Now, is this continuous? Is this, okay, differentiable? I cannot ask because I don't have differentiable structure here. I just have a topological structure. So is this continuous, for instance? And the answer is no. We can see an example. So let's see that f of x equals our favorite 10x mod 1, the decimal expansion. We know from everything we know from kx mod 1, from what we have seen, that the entropy of Lebesgue equals log 10, okay? This we know. Lebesgue, the entropy of 10x mod 1 with respect to Lebesgue is log 10. Yeah. And now, so if this guy was continuous, you would see that any sequence of measure that is converging to Lebesgue would have the entropy would converge, would be sequentially continuous because, yeah, because we check that this is a metric space. This is a metric space, so to prove continuity, it's enough to prove sequential continuity. Okay, also to break continuity, it's enough to break sequential continuity, okay? Now, see that, let's take this set, Fk, K below here, for K in N, Fk is a set of fixed points of Fk, set of fixed points of Fk. Do we know what are these fixed points of Fk? Yeah, to know this, first of all, let's see that the fixed point of f already for k equals 1, okay? We know that f has 10 fixed points, okay? F has 10 fixed points. Okay? You can just see them by just writing. I should have 10 of them. I will not draw the 10. So, and you draw the diagonal. You see the intersection with the diagonal, and that counts you the number of fixed points. F has 10 fixed points. And f squared has 10 squared fixed point because you can just see that this will be 10 square x mod 1, and you will have, 10 square branches, and every branch will intersect the diagonal, and so on. So Fk has 10 to the k fixed points. So the cardinality of this set Fk is just 10 to the k. Okay. Yeah. Now we can define. So this is what we have. What I just discussed here. You can define a family of measures that I just Dirac delta on these guys. 1 over 10 to the k yeah, easily you can see that support of mu k is just fk, sorry, fk, and cardinality of fk is finite, okay? Cardinality, we know, yeah, that's. So this would imply that the entropy of these guys will be 0 because you will be, when you're doing the sum, you will be evaluating on a finite set, and yeah. So this implies that the entropy of mu k respect to f is 0. Okay? And I urge you, or I ask you to check this as an exercise. We don't do it here, we know already how to do it, that these measures are converging to Lebesgue and the weak start topology. Mu k is converging to Lebesgue star. Yeah, you can just do it. So if you want, you can do it using Riemann sums. There are many ways to check this. I don't know. Maybe we have done these exercises before in the previous lectures. Anyway, so this tells you that, and this guy, they have 0 entropy, is 0, and this guy has log 10. So the entropy is not continuous. So this guy is not continuous. Okay. There are some very special cases where you have continuity, even differentiability of the entropy, like when you consider certain, like the geodesic flows, negative curvature, but you're not changing, you're changing the metric. So, special case. So when you have the geodesic flow, Ft is the geodesic flow, in negative curvature, you can check that this map is differentiable. It's not you can check, you cannot do, I'm sure. Yeah, this was proved by, this is a research paper by Polycott and Knippel. So this is a metric, so this is a Riemannian metric. And mg is a Liouville measure, okay? This is something we haven't seen probably in this course. Liouville measure. But this is a very special case because you're not changing the measure. You're changing the metric, and if you're changing the metric, you're also changing this guy. So the problem here was you fix your dynamical system and you change the measure. Here, you're changing the metric, so in which case you're also changing your geodesic flow, and also you're changing your measure in a very specific way. You just consider the Liouville measures, okay? So if you do that, you will have that the number, this real number, will change in a differentiable way. But in general, we have this theorem that let P be a partition of finite entropy and it's not like a crazy partition. The boundary of the partition element has 0 measure. Then this is some upper semi-continuous. is upper semi-continuous. Okay. What did I do? Sorry. Shit. Yeah, I don't know. Yeah. Yeah, let me just comment a little bit about expensive maps before I close today. So, definition. A homeomorphism F is expensive if there exists epsilon 0 positive, such that for all x, y, and m, if these 2 points they stay nearby for all time, the distance between f and x, f and y, is strictly less than epsilon 0. For all n in z, then x equals y. Okay. Yeah, I write the definition for homeomorphisms here. So because I'm taking, yeah, so that's how it is defined. So you take, if point they stay nearby, both forward and backward, they should be equal. And that is the expensivity constant. Okay, epsilon 0 is the expensivity constant. Okay. So for instance, see that this epsilon 0 should be at least less than the diameter of your space. Okay. So think of epsilon 0 being something small in general. Okay. And yeah, examples of expensive maps are like non-expensive map. First of all, you see that the translations, like circle rotations, are not expensive. Okay, circle rotations are not expensive. Last time, I mean, in the previous lectures, we have been doing something like this guy, 211 on the torus. Last time we were proving mixing and some properties of this dynamic system. This guy is expensive. Now, how is expensive going to help to calculate the entropy? So let's close with this proposition here. Proposition. Let F be expensive. And epsilon 0 be the expensivity constant. Yeah, the expensivity constant. So that's that epsilon 0 that we have in the definition. Then you have the, so given a partition, so given a partition P with diameter of P less than epsilon 0. So these are the diameter of the partition elements, and diameter of Pn also going to 0, then this is what I want to say. Then, given a partition with diameter of P is less than epsilon 0, then the diameter of Pnx goes to 0 as n goes to infinity. So it's a way to check this condition that the diameter of the partition element goes to 0 if you have expansivity. So in particular, we have that the entropy of F is the entropy of this partition. So Pn is the one you get from the dynamics, okay? When I put n above here, superscript is what you get from the dynamics. H mu of F Pn. Yeah, so today's lecture, we stop here. We will, on Wednesday, we will meet again on Wednesday. We will be taking the proof of this and then do examples now about the Gauss maps and other dynamical system that I will propose. So we will be seeing how to calculate entropy of certain dynamical system that we have been seeing in the course. And also, we will discuss the Shannon-Macmillan-Bryan theorem, which is also another tool to calculate the entropy beside Kolmogorov-Sinai. So that's what we will see in the next lecture. Probably we do entropy on Wednesday and also Friday. And next week we will start the chapter about variational principle. And so we will close next week. So we will discuss variational principle next week, and also I plan to discuss a little bit about expanding maps in general to close this course. So for today's lecture, we stop here, and I will see you on Wednesday.